Thank you. Good afternoon, everyone, and thank you for attending my session. I know it's getting towards the end of the summit, so I really appreciate the energy. So today I'm going to be talking about Zynga's first portfolio-scale machine learning project. What that means is we're actually building hundreds of models every day for dozens of titles in our portfolio, and we're doing so by taking billions of records of data and creating these useful signals that we use to improve engagement in our games. So the two enabling technologies we have are really this library that we're using for automated feature engineering and Pandas UDFs, which we're using to actually unlock a new magnitude of processing power for a Pandas library. So I'll talk through what our motivation was and how we overcame some challenges with this workflow. And hopefully you can actually take some lessons learned from what we're doing with PDFs in your own organization. So before I get started, show of hands, who's actually used Pandas UDFs before? All right, who's used the grouped UDFs functionality? Hands still up? Okay, a few people. And then has anyone actually used those in production? So any other? I don't see any hands. So we'll show a use case where we're actually doing this, and hopefully this provides a viable opportunity if you need to use something that only works with Pandas. So Zynga, if you haven't heard of it, is a mobile gaming company. We make a lot of our own games, but we also have acquired some studios recently, so we have a rich portfolio of games. The image here is from our analytics team at Zynga, and we're actually spanning our central tech and central data organizations. And the photo here is from our annual internal analytics conference. It's called Dog Days of Data, and we flew people from all over the world from our many different studios to our San Francisco headquarters. The goal was really to share learnings and kind of level up our analytics capabilities. So this was a really fun event, and it brings all these teams together. Our analytics team is comprised of three groups. We have our analytics and engineering group, which is really responsible for our data platform. So they handle data ingestion to data warehouse, data lake, as well as powering live data services with our data, such as personalization services. We have our embedded analysts, which are co-located with our game teams, and they actually pair up with product managers, with producers, and even GMs. And really, their goal is to help improve our games. They might understand things like how a change in one of our games, a feature change, actually impacts the game economy. So we have things like slots games where you need to understand how changing something might impact, say, the payout in a slots game. So it's very valuable to be able to model that out before we actually roll something out. And then the third group, which I'm part of, is our central analytics group. And this is really focused on publishing functions, things like marketing, advertising, and corporate development. And really the goal of this team is to build analyses and data products that can scale our portfolio. So ideally, anything that we build, any of our different game teams should be able to plug into their system. So that's one of the goals we have. So as I mentioned, we're a mobile gaming company, and we have this rich portfolio of titles. Here's some of the games in our collection of franchises. CSR2 is an acquisition from a few years ago from our Natural Motion studio based in London. It's a racing simulation game. We have Wonka's World of Candy, which we released last year, which is a match 3 game. And we also have our forever franchises, things like Words with Friends 2 and Zynga Poker, where we have been iterating on these franchises for a while, and it continues to be kind of a core piece of our portfolio. But it means we have a variety of different types of games. We have our recently acquired studios of Gram Games and Small Giant that produce Merged Dragons and Empires and Puzzles. And these are kind of interesting games that are match 3 plus action adventure games that kind of blend genres. So we have casual card games. We have these wordsmithing games with friends. We also have games just based on our Farmville IP that we continue to develop. So the challenge is that we want to support our game teams to basically act on their data, but we have a variety of different types of games. So you have different kind of specificity of events. So a casual card game will have things around hands played, while a match game will have things around levels completed. And we basically want to build these predictive models for whatever game that we're acting on. So I've kind of alluded to this, which is really that we want to build more predictive models that provide signals for personalization in our games. So if we want to build these segments of different users to target with different treatments, we want to have a variety of signals that game teams can use that are in addition to just kind of heuristic knowledge they have. So they might know that people that have played X number of sessions over the past couple of days are more likely to engage with a certain feature, or if they have the low number of sessions, they might drop out. But really, we want to provide a predictive signal of whether they're going to perform those actions. So things like understanding whether a user is likely to make their first purchase or whether they're likely to churn from the game is very valuable when we actually try to add personalization to improve engagement in our games. So our goal is to build a lot of game-specific models that have kind of diverse event taxonomies. So in a match 3 game, you're making moves. We can track what moves you're making. We can track your level completion rates. We can track your scores, and basically how well you're performing in the game. But that's specific to match 3 games. If you then switch to CSR2, which is a racing game, you have races completed, you have customization options, and it's a completely different event taxonomy. So we need a generalizable way of creating these predictive models that works across our portfolio of titles. And we also have a challenge with scale. So we have a number of different platforms we support. We're mobile focused, so that means iOS and Android, but we also have some web applications. We have dozens of games, and we have tens of millions of daily active users. So there's a lot of combinations of things that we need to support in order to really build this portfolio scale project that can pretty much automate this whole workflow. So we've actually been able to use a few tools to accomplish this. And the first is tools to get to automated feature engineering. So we're actually working with structured data. We have events with well-defined schemas. So it's not a deep learning problem. It's more of a shallow learning problem. But we still want to borrow from deep learning methodologies in terms of automated feature generation. So we're using a library called Featuretools, which operates on Pandas data frames, which allows us to automate a lot of the manual data science workflow that we had in the past. And now, whenever a new game launches, we basically can plug up the system, and it knows how to go about generating a useful space of features for input to our models. So this allowed us to automate that step. The next step was really scaling that up. So before we can actually productize this and score tens of millions of users every day, we needed to go from a kind of single-threaded Pandas-focused project to something that can actually work at scale. And we've done so with Spark using a functionality called Pandas UDFs, which is a relatively new feature that I'll focus on a bit, mostly during the second half of the talk. And the third enabling technology is really PySpark and Databricks. So we've been using the Databricks environment, which has allowed us to rapidly go from prototype to production. And it's been a really great kind of collaborative notebook environment that's really eased the transition from writing scripts in Python to making those scalable in PySpark. So we've used these tools, and that's actually enabled us to build this kind of portfolio-wide data product. Our name for this system is AutoModel because it basically automates the process of building propensity models in our system. So this is a portfolio scale project because basically it takes game data in from everything, does some transformation of the data, and creates these kind of game-specific predictions, even though there's not a bunch of domain-specific knowledge that's encoded in the system. So it's something that we can basically plug in new games and have it scale as needed. It provides a number of useful signals that our product managers can use when defining segments, and we're getting more sophisticated in the types of treatments and segmentation we can do as we have more signals that are available. And the end result of this really is to empower our game teams to make kind of more engaging experiences. So that's either powering features directly in the game or things that might be on the back end, such as live services. So if we know that a user is likely to churn, but they have high affinity for Zynga games, we might cross-promote them instead of showing a third-party ad. So there's all sorts of opportunities we have to basically personalize our gameplay experiences based on this knowledge that we have available. So here's an overview of the components in our AutoModel system. And really, this will be the structure for the rest of my talk. I'll go through kind of each of these components in more detail. The first phase is basically getting the data. We have a data lake that's set up where we actually start this process. The next is where we're working with a sample of data, and we're doing the automated feature engineering. The third step is scaling up to our whole user base. So now we know what feature transformations to apply, and we now want to do this on our full data set. And then the fourth step is using MLlib to basically build propensity models based on this wide feature space we've created. And then finally, we publish the results to our application database. Once we've done this, our game teams can start using these scores in production. So what's great about this approach as well is that it's allowed us to have our data scientists build end-to-end data products, and that's been really powerful for us at Zynga. So the first stage is extracting our data from our data lake. Our analytics engineering team is responsible for making sure that our diverse set of game clients come through a single data pipeline that then becomes available in our data lake. We're built on AWS, so the majority of our data is stored in Parquet format on S3. So we have most data come in through a kind of raw event format where it's schematized, but it's standardized across games. And then we have later ETL pipelines that actually split that out into game-specific data models. But I'm actually taking advantage of this kind of staging raw data because it's a source where we have all of our game data and we have all the events and it's not aggregated. So it's a nice, rich data source to start with, as long as you have a good way of transforming it. So really the first step is to use Spark SQL to transform that data a bit, and the end result of this phase is some Spark data frames that we then begin the workflow with. So the next step is where we're actually doing our automated feature generation. And this is really trying to replace a lot of manual work we were doing for our data scientists in the past. So we're using this library called Featuretools, which I'll talk about in more detail. And this basically allows us to say, here's a deep but narrow format. We want to create a shallow but wide format that we can then use as input to our predictive modeling framework. So it's a tool that we've actually been able to use to automate this process. So the way we used to build models at Zynga was a data scientist would be given a task such as building a likelihood to lapse or likelihood to churn model. And that data scientist would use their kind of game-specific knowledge. Say they worked on CSR2, which is our racing game. They would add all sorts of usage of different features to understand, come up with a nice encoding that probably provides good signals for a kind of classification model. So you might encode things about how many times they're active, which features they're using, what their win rates are or success, whether they're doing kind of player versus player or other types of game modes, whether they're single or multiplayer focused. And the result is you often get these really rich representations that encode a lot of game knowledge. It just takes a long time to get there, and it means that every new model is this one-off process that takes a while to iterate on. So what we've done is basically use this library to do that process of exploring the data in our taxonomy in a much more automated way. So instead of a data scientist saying, count the distinct number of days played, find the maximum score or average score, we have a tool that basically allows us to explore these different combinations. So as I mentioned, we have this raw staging table with just kind of a narrow representation where you have a player, a category, a subcategory, and a number of values. And we can actually throw anything in there, but it means we need to decode that into a nice representation at a per player level that we can then throw at our predictive modeling. So we're using this approach to handle the fact that we have these diverse event taxonomies, and we're trying to replace this manual workflow of writing Spark SQL or writing just general SQL in order to do that transformation. We want to do so in a programmatic way that works across our entire player base, and we want to do so in a way that scales up to billions of records every day. So Featuretools is a library that really helps us accomplish this, and it's something I stumbled upon just doing some Google searches of automated feature engineering. So it was lucky to come across, and it was interesting because there's a lot of research out there really focused on this feature engineering step, and some people have even called it kind of the holy grail of machine learning is figuring out how you can generate features that you then throw at your modeling systems where you do the fitting and hyperparameter tuning. So there's nothing really magical about this, and the name deep really comes from the fact that you're chaining events together at different levels of detail. So you have tables that point to other tables, and the types of aggregations you're doing can chain together, which makes this kind of representation that's nested. So maybe nested would be another term to use rather than deep here. Another distinction from deep learning here is that we're working with structured data, and the idea here is to create a space of features, but you're not performing model fitting at this point. You're basically taking input data and trying to translate it into a different representation where you then can do, say, clustering or classification or regression modeling from. So the base data set that this tool or this library uses is called entity sets. And entity sets are a way of describing your data, which is generally going to be a set of tables and representations between them. And you can think of this almost as tables and foreign key constraints. So in our case, we basically want to make a representation of a player where we have events and sub-events that we want to describe. When you run this on your data, basically the result you get is a set of feature descriptors. And these basically tell you how to apply transformations on new data frames so that you can reproduce this transformation of narrow to wide data representations. So once you've done that on a sample of data, you can then do that across your whole user base if you have a way of scaling it. So as I mentioned, the representation used by this library is called entity sets. And basically, it's a set of tables and their relationships. So this slide shows an example where you have a customers table and a transactions table. And you say that each transaction has a customer ID that points to that customer. And each customer can have 0 more transactions. In terms of the actual data frames, the input here is a customer frame, which has 3 attributes and 5 entries, while the transaction table has 5 attributes and 500 entries. So this means that there's customers that are probably making around 100 transactions in this example data set provided from Featuretools. So once you have your entity set, you then can tell Featuretools to basically convert it from a narrow to wide representation. But it needs to know kind of the relationships in your data in order for that aggregation to be performed. And this data structure is what's used to specify that relationship. So once you've represented your data this way, you can then perform deep feature synthesis. So here's some Python code that shows how this is done with Featuretools. You first import the library, and then in the next step, you say perform deep feature synthesis, which is the DFS function. You specify your input entity set, which is ES here, and you specify your target entity. So in this case, you say you want to roll up the transactions and customer data tables into a single customer summary table. And the result of this function is shown below, where we sample 5 of the rows. You'll see that there's attributes that correspond to the customer, such as the ID and the zip code. And then there's aggregated features from the transaction table, which was kind of a child table of the customers table. So what this means is it actually performs aggregations, such as the number of transactions that the user has, or the total amount of transactions. And what this does is it provides a wide space of transformations you can make to your input data that you can then throw at a modeling technique. For anyone worried about GDPR, this is not our data set. This is a sample data set from Featuretools. So just a note to make there for our legal team. So we've actually used this, and we've done kind of a two-phase transformation, where this is showing first a one-hot encoding that we use to basically take our data and make it a bit wider, where we take things like the category might be level complete, the subcategory might be level objective, and one of the values might be the objective type. So in a match game, this might be clear X gems, it might be uncover certain tiles, or it might be clear a path of tiles for a character to traverse. So we actually are able to expand that from, say, 3 values for a single attribute to 3 attributes with just a binary value. So that's pretty standard. There is a bit of transformation here where we actually take our input data frame, which is raw data DF. We actually perform deep feature synthesis at depth 0, and then we call encode features. Really, the reason we're doing this first step is just to get a set of feature descriptors that are needed for this encode features method in Featuretools. You can probably use other utilities in Pandas just to do this transformation directly. But it's a way we've been able to basically do our sampled and full-scale data using the same transformation. So I've omitted one of the steps here, which is really how we set up the entity set representation. So we have a user, a category, and a subcategory. And we actually break that apart into 3 tables, where subcategory events point to category events per user, and those per category events point to a player. And this allows us to have this nested data structure that we can then do deep feature synthesis on. So that's actually what's shown in this second step, where we take our one-hot encoded data frame, we then pass it to this deep feature synthesis method where we say the depth is 3. And that means it's going to take our user data, traverse to depth 2 at the category level, and then traverse to depth 3 at the subcategory level. So you get all sorts of combinations, aggregations. And the result of this is basically that we've been able to go from just a few columns to hundreds of columns that summarize a user. So we might have 1,000 attributes that describe a user. We've basically been able to collapse that into a single record with a wide number of columns that are useful for throwing into your standard classification regression methods. So we actually did this with a sample of data and found that in some of our models, we were basically able to achieve kind of similar model performance versus some of these handcrafted models. Due to like the free lunch theorem, you're not necessarily going to do better than everything, but we found comparable performance, and we really were excited to roll forward with this and scale it up. So we had a few approaches that we were thinking about and tried. The first was basically, we want to do this for every game. What if we just do a different thread per game? But you still end up with this process where the data frames were too big to fit into memory, given that entity sets are backed by Pandas data frames, and we're trying to run everything on a single machine. So we thought about maybe breaking it up. You could have groups of users versus a single set of training, but you still run into this problem of handling fault tolerance, orchestrating all these different threads, potentially trying to distribute the workload and have it work together in a seamless way. And it just became kind of too daunting of a task. So the next approach I tried was really using Spark SQL. So this was actually taking the feature descriptors that are provided by Featuretools that tell you how to transform your data set and converting that into Spark SQL code. And this worked in concept, but it was very slow. And as we scaled it up to hundreds or even thousands of aggregations, it really became a bottleneck, and it wasn't tenable to scale up to our full-scale data set. So we needed a new approach. And what I stumbled upon was a new feature as a Spark 2.3 called Pandas UDFs. What Pandas UDFs allow you to do is basically do distributed Pandas operations across worker nodes in a cluster, but you don't have to manage that orchestration yourself. You're basically able to leverage Spark to partition it, do the translation between Spark and Pandas, and worry about just writing a function that operates with Pandas. So for a data scientist, it's as if you're working with Pandas data frames. So it sounds like a few of you have used Pandas UDFs. A lesser known feature is grouped map operations, and this was something introduced as a Spark 2.3. Basically, what this allows you to do is to partition a Spark data frame into Pandas data frames across your cluster, write functions that operate on that, and then to take the results back. So as long as you can partition your problem in a nice way, you can use this feature to do distributed Pandas computation. And it means that a lot of libraries that weren't developed to operate on Spark actually can operate on Spark at scale. Here's a visualization of what this actually looks like. So we have our raw input data frame, which is a Spark data frame. We tell it to partition by user or group of users. And then this gets distributed across all of our worker nodes. This translation between Spark and Pandas is done via PyArrow, so it's pretty efficient. The code that you write is really this function in the middle, which is your user-defined function. And we use this to basically say, take the input data frame, apply feature tools to it to translate into our wide representation, and return that result. The output of the function is Pandas data, UDF, or it's a Pandas data frame, which is then joined together into one large Spark data frame again. So the resulting data frame you can use with MLlib and other Spark tools that you need. But it's a way of decomposing a problem to operate with Spark data frames. So there's a few cases where these are very powerful. If you need to operate on a library that is dependent on Pandas data frames, and you have a good way of partitioning your data so that you can do a divide and conquer approach, it's a good fit. For something like Bootstrap analyses for experimentation, it wouldn't be a good fit because you need to randomly sample across the full data set. But if you can decompose your problem into smaller problems, such as scoring an individual user, then it works out pretty well. The other prerequisite is that you need to have your data represented as a single Spark data frame. So when you do the partitioning, you basically have that single frame that's split up and then passed to your function. You can use broadcast variables, but you can't necessarily pass multiple Spark frames to your UDF. So you need a data set that's represented as a single frame for this to work. So here's an example of what a UDF actually looks like, and we'll step through a few different pieces here. In the introduction post on Pandas UDFs, they use the ordinary least squares method in stats model. For this, we'll use the least squares function in NumPy. The data set that I use for this is the Kaggle NHL data set, which describes basically a number of players and their performance each game. Some of the attributes are the number of shots they took, as well as the number of hits. I was basically just trying to do a linear regression fit to see if there's some sort of correlation between, say, being aggressive and actually having more shots on goal. I didn't really come up with a conclusion there, but what I did do was distribute this workload across a cluster in Spark. So to start, you need to specify the output of your UDF. And this is actually describing what gets returned from your function. Here you're actually describing it as a Spark schema. So you as a user writing the function actually return a Pandas UDF or a Pandas data frame, but you need to describe the schema as a Spark data frame. And this is something that needs to be known ahead at execution time before you actually go about calling your function. The next step is basically telling your Spark data frame how to be partitioned. So in this data set, there's a player ID which describes each individual on the roster for a specific game. So we're actually going to distribute each player into a separate Pandas thread of execution, which gets used for distributing the workload. So there's some trade-offs with the partitioning you use here. If you partition every user across millions of users, you create kind of too many partitions. If you create too big of partitions, then it might not fit in memory when you try to reload it from PyArrow. So this is something that actually requires some tuning when you actually throw this to production. The next step is it calls the analyze player function, which is defined here. And this is where we're actually taking an input Pandas data frame. So player PD is a Pandas data frame that we are operating on. And at this point, we can actually call NumPy or any other functions that operate on Pandas data frames directly. Here we're getting the result, which is a set of coefficients. And then the final step is actually returning a pandas data frame. So this is basically taking those coefficients and then returning them at a ID and beta 0, beta 1 kind of coefficient here. Here we're returning just a single row, but when we get back to that last step of result Spark DF, it's going to return a single row per player. So this is a case where we've gone from kind of a deep to shallow representation, and we've transformed it for each of the players in our data set. So I've talked about how we do our one-hot encoding and then our feature transformation. And this slide shows how we combine that with the Pandas UDF. So again, I've kind of omitted some of the translations we do to get from our data set to this entity set representation. If you're interested in looking at what that looks like, I wrote a Medium post with the Kaggle NHL data set, which shows how to do that kind of nested structure representation. So the key thing to call out here is we have at the bottom a user group where we bucket users into, say, thousands of different buckets. That allows us to take the billions of records we have and split it up into something that fits into memory. We then call the apply feature generation step, which takes a pandas input data frame, and at the end really calls calculate feature metrics, which basically applies our feature transformation from before. So we pass this our entity set, which uses the pandas data frame, but we also pass it this object called saved features, where saved features is the list of feature transformations we performed during our training step. So this is actually a broadcast variable that was basically on the driver node, but is being passed to these UDFs. So while you can only operate on a single data frame, you can actually use different scope variables within this function if they're broadcast. So it's not completely outside of side effects, but you can use broadcast variables, which is useful for things like this feature transformation. So the result of this is basically that we have our raw input data. It gets transformed into a user level summary. And then as a result, we basically have a list of users with a very wide representation, which you can then throw at your favorite classification or regression method. So this is great, but Pandas UDFs aren't without some flaws. And as you start really digging in and trying to productize these, you might hit some of these edge cases. One you'll just see while actually starting to use these in your workflows is that debugging can be really a challenge. So when you're actually operating within a UDF, you're executing on worker nodes, which means that print statements no longer work. So instead of operating with just a driver node where you can actually see the flow of execution, you actually need to go to your Spark logs to figure out what's going on when you see an exception. We also were kind of pushing the limits of PyArrow, so we're scaling billions of events across these clusters. And we were using an older version of PyArrow and found some edge cases and some issues that were on GitHub that are now resolved. And we actually fixed some of these issues by just upgrading PyArrow. But Pandas UDFs are a newer function, and you are going to hit some edge cases. So just be aware that it is kind of newer tech that is still being developed on. One of the edge cases we hit was with data type mismatches, where there was a half float or float 16 type that couldn't be cast to a Spark data type because there wasn't a corresponding issue. So we had to basically manually cast some of our data types to get this to work. So it's not just a kind of replace your pandas code with UDFs. You do need to have some concerns around what goes on here. And another limitation is that the schema needs to be known before the UDF is computed. So we do a kind of sampling step where we actually figure out what that feature transformation is that we want to apply to all of your users. But if you're actually trying to do feature generation within the UDF, that wouldn't work because you don't actually know what the schema is yet. So there are some issues with Pandas UDFs. And I was really excited to see the announcement with the Koalas library yesterday, because that could be an alternative to Pandas UDFs, where you could actually take Featuretools and try to get that to work with Koalas rather than taking Featuretools and trying to get it to work with Spark. So the output now is a representation per user with hundreds to thousands of features. The next step is to take MLlib to create propensity models for all of our users. So we also create a set of labeled examples where we know whether a user is likely to churn or not, or make their first purchase in the game, and then we throw that at MLlib. We use kind of all the standard methods here and won't claim that we're doing anything highly novel here. We basically try an ensemble of different algorithms. So for each model that we're building out, we'll try logistic regression, random forest, gradient boosted trees. And we're also using XGBoost, even though that's not really natively supported by MLlib, but we found a good wrapper for that that allows us to use it within this workflow. We then also do some parameter search, hyperparameter search using the grid builder and cross-validation. And we basically pick whatever algorithm has the best cross-validation score. So the actual algorithm being used to create predictions for our users might change day over day for our different games or for our different models. So we actually provide kind of a rank of what the prediction is rather than the raw scores to prevent analysts from kind of misinterpreting what's going on there. But the result is we basically have a collection of propensity predictions basically that we can use to create these custom segments for our game. The final step is basically pushing this to our application database where our game teams can make use of it. So we have a system built on Couchbase where we basically have a function that was put together by our analytics engineering team that allows data scientists to push scores to the system. And they've done it in such a way that it's asynchronous and won't make the cluster fall over, which is great, because data scientists like me will sometimes make mistakes. So one of the things we've done this to actually productize this and scale it is we're actually using some of the custom functionality with Databricks to use the jobs API. So one of the functions we used initially was just the ability to call notebooks from other notebooks. We have kind of a driver notebook that spins off a notebook per game. And what we found is we could actually get kind of better stability and scale if we actually call off different clusters. So depending on the mode of execution we want to run, we can basically have a bunch of parallel notebooks, or we can actually have a bunch of clusters that run. And the cluster approach allows for a bit better isolation, and if we need to rerun the model, we can rerun it for a single game versus a whole set. But this was a really cool way of actually integrating kind of infrastructure management within a notebook itself, and it's allowed us to basically do these large-scale end-to-end data products from a data science team. So I've been using Pandas UDFs for Featuretools, which has allowed us to build this really cool end-to-end data product. But we found other uses of Pandas UDFs at Zynga as well. So our game analysts have built up this experimentation notebook that allows us to do A/B testing and other types of analyses. And we've actually found good use cases for distributing stats models, Scipy, and NumPy. And none of these were kind of authored to work natively with Spark in a distributed way. But with Pandas UDFs, you can actually enable that as long as you have a way of distributing your data in a nice way to kind of take a divide and conquer approach. So we've actually seen a bit of a kind of changing landscape in Zynga in terms of our data science and machine learning capabilities. As I mentioned, we had kind of this old approach of taking weeks to do manual feature engineering. You would then work with an engineer to try to figure out how do we get this in production, and then figure out, well, do we actually monitor it or not, or just kind of YOLO, throw it to production and hope it works. This had some wins, but it's not where we want to be. Where we're moving towards is a world where most of the workflow is automated. So if a new game comes online, we can just throw a new game ID into our system, and it knows how to go from there. There's no custom work to productize models. Everything goes to our application database. And we have monitoring in place to make sure that our performance metrics are being monitored. We're not using MLflow yet, but that's something we're excited to really integrate into this workflow. So we've built this cool product using Pandas UDFs, and I think it's something that a lot of teams could potentially use. There's all sorts of developments going on in the Spark ecosystem, making Pandas more like Spark and Spark more like Pandas, just to make it easier to use these ecosystems for data scientists, while also making sure that we can operate at huge scale. So Pandas UDFs are a tool that we've used to basically unlock a new order of magnitude of processing when using these tools based on Pandas. And the second takeaway is that it's enabled new types of machine learning capabilities at Zynga. So this isn't something that we were previously able to accomplish that now is possible. We're able to create these hundreds of models every day that power services for our games and enable us to take less time going in the weeds and trying to perform kind of model tuning and actually talking with our game teams more and figuring out how we're going to use these predictive models. So because of that, it's really been a game changer for us. And it's been really useful for kind of leveling up our analytics capability as a whole at Zynga. So that's Pandas UDFs. I hope you found some use cases that might apply to your organization. And I'll now open up for questions. Thank you.
Thank you, Ben. If anybody has got any questions, there's a mic out here. You can come and ask. Thank you.
Hello. When you say, when you went back and said like there is a broadcast, being able to broadcast variables at each node, we have been facing some challenges in using variables that are actually declared at global scope versus that is declared at a class scope. And if you have a Pandas UDF defined in the Python class, then they don't generally get that context from the class level. So can you perhaps a little bit talk about how are you using the broadcast, and maybe share some details on that?
Yeah, so for our case, we're using pretty lightweight objects. The feature descriptions is basically a list of about 1,000 kind of trivial operations. So we're not actually doing any explicit broadcasting there. It just happens to work the way we have it set up. So it is just a global variable that is working in that context. In terms of doing the explicit broadcast, that's something we haven't dug into too much yet and would need to do some additional testing on.
So it is just a global variable that becomes
Yes.
Becomes available in the Pandas UDF context.
Yeah.
Okay. Good. Thanks.
Any other questions? Go for it.
So when you try to push the model to the database, so do you have to do anything to try to modify the model? Because for deploy, you always use some how to deploy it? Is like pure Python, or it will translate to some Java, or what?
Yeah, so for the push to our application database, it's basically a data frame where you have a user ID, kind of an attribute, and then a value. We actually have a method that basically publishes that data set to, or just saves it to S3, and we call a different function that asynchronously loads that via a different Airflow job that's not managed by that notebook itself. So that's done via EMR and not part of the data science workflow.
But it's the regression is easy like a weight. It's easy to deploy, but it's like an XGBoost, probably tree based. So you still have some way to pass in for the prediction on the prediction side. Doing a prediction.
I can't really make that out because the speaker's over here, but I can chat more after.
Okay.
Hi, I have two questions. So the first question is, how widely is Featuretools being used currently? Like, how many different scenarios are you using Featuretools?
It's primarily being used for this tool, but there's other use cases we're exploring as well. So being able to do clustering in kind of a game agnostic way is something we're exploring, as well as things around anomaly detection, fraud, all sorts of use cases where you're doing kind of tree classification models. So this is the one where we're using it in production, but in terms of our game analysts, there's a lot of scenarios we're exploring as well.
And you're exploring that with Featuretools?
Yeah, for basically translating from the raw to a wide space of features to use as input.
Gotcha. And once you expand that feature set into like thousands of features, do you try to apply any feature selection techniques?
At this point, we haven't done that explicitly, but that's something that we'll throw into our modeling pipelines as more teams are kind of picking it up.
Do you feel like it's going to be a little bit challenging to explain the model that way because you have thousands of features?
Yeah, and that's one of the challenges we've had is generally people will show it to their game teams, and then the game teams will ask, can you describe how this works? And really, it becomes pretty opaque with some of the encoding you've done. I think that'll be kind of a follow-up project where some of the analysts will actually try to kind of reverse the encodings into explainable game features.
Okay, thank you.
Oh, thank you, Ben. That was an amazing session. Thank you all.